Hello everyone. It is my great honor to present our recent work on test case prioritization for deep neural networks. My name is Zhan Wang. This work is done by myself and my colleague Professor Junjie Chen, Professor Xuyuan Dong, Dr. Wenbing Zhang, and my students Han Mo Yu and Yingyi Zhang. We are all from Tianjin University in China. Deep learning techniques have been widely used in safety-critical applications such as autonomous driving, medical diagnosis, and some other applications. Poor quality in this system will endanger human lives. Therefore, it is imperative to guarantee the quality of DNNs. DNN testing is one effective way to guarantee the quality of DNN by validating the model on numerous test inputs to measure its accuracy. Before testing, large amounts of labeled inputs are usually needed, which will raise a key challenge. It's very costly to label test input to check the correctness of DNN prediction. How to reduce the labeling cost has attracted a growing attention from both deep learning and software engineering research communities. Researchers have proposed many techniques to reduce labeling cost, among which test case prioritization is a useful way. It prioritizes test inputs so that those inputs which have more chance to reveal bugs in DNN can be labeled earlier. In this way, more bug-revealing test inputs can be identified in a limited time, and these valuable inputs can be used to conduct the model debugging and fixing process earlier, which could largely accelerate the entire DNN testing process and shorten the period of DNN development. Two main test case prioritization methods are confidence-based techniques such as deep joining and supervised adequacy-based techniques such as LSA and DSA. Although these methods have been demonstrated to be effective in some cases, they actually suffer from the effectiveness issue or have limited application scenarios. Due to the limited time, please refer to our paper for more detailed analysis on this. To address the issues above, we proposed PRIMA, a novel test case prioritization techniques for DNN via intelligent mutation analysis. To identify bug-revealing test inputs, PRIMA adopts both model mutation and input mutation based on two key insights. The first is for model mutation. If a test input can kill many mutated models, it means those inputs can test and explore DNN sufficiently. The test input is more likely to reveal DNN bugs. The second is for input mutation. If many mutated test inputs are killed by original model, it means the information of inputs are sufficiently used and explored. The test input is more sensitive to capture DNN bugs. We regard test input with higher exploration to themselves and the DNN model as the bug-revealing test inputs. Let's look through the framework of PRIMA. In mutation process, we design mutation rules for both DNN model and test inputs. Then PRIMA extracts features from mutation results and uses this feature to guide further prioritization. Moreover, PRIMA incorporates learning to rank to build a ranking model based on derived features to prioritize inputs. After that, the result can be transmitted to developers for labeling and further debugging. Then we design a series of mutation rules in PRIMA. The main idea of design mutation rules is to slightly change the basic elements to see if the changing part is sufficiently explored and utilized in prediction. Since neurons and weights are basic elements in DNNs. We specifically designed 4 mutation rules according to previous work, including adding noise to neuron weights, shuffling the connection weights of a neuron with the previous layers, inverting the activation state, and eliminating the effects of a neuron on the next layers. As for input mutation, the basic element varies from different domains. In this work, PRIMA considers 3 popular domains, including images, text, and predefined features. But it is easy to extend PRIMA to more domains. For images, the basic element is pixel. We designed 5 mutation rules, including adding noise and some other operations on pixel. For text, the basic element is character. We designed 3 rules, including shuffling characters, making typos, and repeat a certain character. For predefined feature, because the basic element is each feature value, we designed 2 rules for continuous and discrete value respectively. We carefully extract 2 kinds of features from the mutation results for further prioritization. They are F1 and F2 respectively. F1 measures the class-related features and F2 measures confidence-based features. Using these features and the ranking model, PRIMA predicts a score for each test input to prioritize all these inputs according to the descending order of their scores. In our study, we evaluate PRIMA on 36 model data pairs as subjects, including 3 domains, 2 network structures and DNN, 2 task classification and regression, 2 types of inputs, 2 training scenarios. To our best knowledge, this is the most large-scale and diverse study in this field. We measure effectiveness of PRIMA by IAUCN. It is the area owned for detecting curve of each method divided by the area on the ideal curve. Larger is better. Overall, compared with the state-of-art prioritization techniques, deep journey and supervised adequacy, PRIMA performed the best in 94% cases. Besides, PRIMA shows superiority on average performance in all 3 domains, especially in the text field. PRIMA outperformed baseline with more than nearly 40% on IAUC 100. What's more, we evaluated scenarios such as transfer learning and polluted training set, where the assumption of deep journey and supervised adequacy are violated, which cause huge plummet in their effectiveness. While PRIMA confirmed the effectiveness in these 2 scenarios. Besides, through experiment on adversarial examples, we prove that once a ranking model through PRIMA is built for a DNN, it can perform well for various sets of DNN. We then investigated the contribution of each feature in PRIMA. We provide a feature contribution list of each task to measure its importance. Still, we proposed a promise optimal method which selects mutation rules that contribute more in prioritization based on the feature contribution list, which can improve the efficiency and only slightly affect the effectiveness. We also conduct practical evaluation on 4 scenario recognition tasks in autonomous vehicle testing. The results further confirm the effectiveness of PRIMA in practice. In this presentation, we first introduced our motivation about reducing labor cost, and then proposed a test case prioritization for deep learning testing based on mutation analysis. We conduct experiments, and the result indicates the effectiveness of PRIMA in finding bug revealing test input. Thanks for your attention.
Okay, hello, and welcome to this session. Thank you, Zen, for your presentation. Very interesting paper. If anybody has any questions for Zen, can you please type them in the chat? In the meantime, I have a couple of questions that I would like to ask you. So just the terminology, can you clarify what you mean by killing mutated models, as well as when you say inputs being killed by mutated models? What do you mean by killing mutated models?
You mean what's the definition of the killing?
Yes.
Well, thanks for your question. This is a good question. As the mutation testing in this work, the prediction result of the new mutant. Well, we just by the result of the new mutant and the original with the original input and original model. If there is different, we can define these mutants are killed. Okay.
Okay. There is a question from the audience from Teodora Baluta. She says, "Thank you for the great talk." And she wants to know, how much do features versus input mutation rules matter for PRIMA's effectiveness?
Sorry, I just did. How much do features effectiveness? And there are two questions about the first one is for effectiveness and the second one is for efficiency.
Yes.
Can I give the answer of the second one? Firstly, because we mentioned the efficiency issue in the paper. To be honest, the efficiency of PRIMA is not very good because we need to generate so many mutated model and mutated inputs. So in our paper, we presented the time spent for the mutation about. I just find the data. The efficiency, the average time spent on test prioritization of PRIMA is about 10 minutes on average, while the baseline method such as deep DNA is only less than 1 minute. Also, PRIMA is less efficient than deep DNA. The cost of PRIMA is still acceptable in practice compared with time-consuming and expensive manually labeled data. So we also mentioned in our paper, this is very interesting and promising direction for the future work. We will find some ways to reduce the cost of the mutation for mutation operators. Okay, the first one is the answer. This is the answer for the first question.
Right. So the one about efficiency. So what about effectiveness? How do features versus input mutation rules for PRIMA's effectiveness matter for PRIMA's effectiveness?
Okay. Thanks for your question. The effectiveness is also important issue for the mutation problem. In this paper, we think both input mutation and the model mutation contribute to the prioritization result. PRIMA provides the contribution of each feature, and it seems that the model mutation feature contributes more than input mutation features. Okay.
Okay. There is a question, more exploratory, is how could PRIMA be used in some other areas?
Some other, this is also a good question, and we do some practical study in image, text, and some predefined features applications. But our model mutation rules are general for various domains. We just need to design input mutation rules for new domains such as speech recognition and some other applications. We can also extend PRIMA to other domains by just determining basic elements of inputs and finding widely used mutation operators for generating adversarial inputs in this area. So, such as we can give an example for speech, because in the speech area, the basic elements is phoneme and the widely used adversarial operator, including adding noise and some other ways to make some new mutants. So we can use these ways to generate the new mutate. Okay.
Okay, thank you. There's another question. This one is from me. I understand you explained that PRIMA is not very efficient in the sense that it requires a lot of time, but the evaluation results are pretty good. I mean, even compared to Deep Genie, which is pretty much like it's become like the baseline. So what is, like, if you were to pick one aspect of PRIMA that is the one that provides these, that contributes to these good results, what would it be? Or did you already answer that question when you said it was model features?
Can you repeat your question?
Yeah.
Sorry?
So why is PRIMA? Basically what I'm asking is why is PRIMA so good? Why does it show such good results compared to Deep Genie, for example?
Okay. I think the most important is the model.
Mm-hmm.
And Deep Genie is a very efficient method for the text prioritization for DNN, but there are some scenario they cannot work well, such as they need much better confidence between the classes, different classes. So it is they don't work well. They don't work well on the lower accuracy scenarios. Deep Genie pay more attention about prediction result, but PRIMA we focus on the state of the model. We just want to know how much the new mutants can be, the input and the model can be explored. Okay.
Okay, thank you very much. We might have time for one more question, and if we don't get to them, you can continue in the discussion room. So there is a question from Yi Liu. He says, did you try the dropout-based technique that can also measure the uncertainty, but is more efficient than directly mutating models?
Sorry. Did you try the drop technique that can also measure? Not yet.
No? Okay.
Not yet. Okay.
Okay, and then a follow-on question from Dora. Yes. A model has a lot of features, a lot of weights, for example. I'm just wondering, how do you aggregate or how do you select which features to use for prioritization?
Okay, this is also a good question. We just use some mutant operator to slightly change the weight. How do you aggregate or how do our approach does not focus on uncertainty. We just use some machine learning methods such as XGBoost to learn from the mutated results to get the ranking model.
Okay. And with that, it seems that we're coming to an end, unfortunately. Thank you very much. See you in the next